All right, so I hope you all had a nice extended weekend. We've got a test on Wednesday, so that's next class period, covers up through what we talked about last week. I did want to go over like at least the starts of a couple of questions related to your iMath AS homework that's due tonight. Just some that I saw people got stumped on more often than others. Just at least start on them and so forth. So one that I saw was from the implicit differentiation homework. There we go. Just put it over here. So you're finding dy dx, and the function was something like this. Everybody's is a little bit different, I believe, on this one. Some of the numbers change, like it's not always a 4, or there might be a minus in there. But generally, it's the same. So the idea with all of this is, there we go, that this is messy or impossible to solve to get y equals and then a function of x across the equal sign from that. So in order to find dy dx, we can differentiate this in its equation format and then solve using algebra to get dy dx isolated. So the idea is when we see in this expression y, think of it as a whole function. And when you see x, remember x is the independent variable. When we're finding dy dx, we're thinking about y changing because of x, or y is the dependent variable, even though in this expression it might not be a function in terms of like the vertical line test or 1y only for each x value, etc. But we can still find the rate of change relationship, which also might not be a function in that same sense. And at any point, though, in the original function, we should be able to find a rate of change if one exists. So if it's not vertical at a point, so we'd have an undefined or something outside of the domain. In this case, square root of x plus y is there. We need to make sure x plus y is something 0 or larger. But when we have this expression, I'm just using blank spot here, square root of x plus y, if I wanted to find a derivative of that, it would involve our square root rule and then chain rule. On the other side, we've just got a sum of a couple of terms, but one of them involves a product of two squared pieces. So when we're thinking of x as the independent variable, or the basic variable like it was in all the things we ran across before, and y as a whole function. So if you want to write this as f of x here, so x plus f of x underneath here, you can do that if that's helpful to keep straight. I'm just going to stick with leaving this as y to save a little bit of writing. But the idea is I've got overall this left-hand side, what is the general type of function? It's a square root of something. So our derivative is 1 over 2 times the square root of that same x plus y times the derivative of x plus y. So the derivative of x plus y has more than one term, so as usual, put it in parentheses. And derivative of x with respect to x is 1. The derivative of y with respect to x is, well, it's called dy dx. Or you could call it y prime. I'm going to write dy dx just to A, keep that in mind, and B, because I tend to lose track of a prime here and there. It might just look like a messy dot. So that's the derivative with respect to x of this expression on the left-hand side, or differentiating the left-hand side of this equation, this relationship between x and y, with respect to x. Now, if we do the same on the right, the 4 part's going to go away, derivative of a constant 0. So all I have to really concentrate on is how do I find the derivative of x squared times y squared, and that's product rule. So the derivative of x squared with respect to x times the original y squared plus the original x squared times the derivative of y squared with respect to x. So this is derivative of a whole formula squared, you can think of it like that. So 2 times that formula, and then chain rule, times the derivative of that formula, derivative of y, which is dy dx. So on the left-hand side, we've got one kind of lump of a term right now, and on the right-hand side, we've got two kind of compound terms, separated by the plus or minus outside parentheses. That's how I'm counting terms here. But dy dx shows up twice. So just as an algebra reminder, if just like you have an equation and x is on both sides of the equal sign, you need to get all the x's together to solve for x. This we're just solving for dy dx. So on this right-hand side, or on the left-hand side, in order to do that, I'm going to think about distributing so that I get this dy dx outside the parentheses, but it's not really too bad. I'm just going to have this 1 over 2 root x plus y, because times 1, not hard. And then the same thing times dy dx. And when you're doing this on your own, you might not write out all the steps, like skip a couple algebra steps if you're comfortable with it, but try to write out as much as I can here. On the other side, same stuff. I'm not going to rewrite all of it. There's nothing to really expand here, but just notice in terms of collecting like terms, I've got 2 terms that have dy dx and 2 that don't. So I want to rearrange to get the 2 terms with dy dx on the same side of the equal sign, just by adding, subtracting, that sort of stuff. And then divide by, or factor out and divide. So what I'm going to do is take this guy, move it over to that side, take this expression here that doesn't have the dy dx in it, and move it over to the other side. So net result of this is, without writing out doing the same thing on both sides of the equation steps, I'm going to have, on the left-hand side, I'm going to have this 1 over 2 square root of x plus y with a times dy dx. And I'm also going to have this term, but now I had to, wait. Yeah, sorry. I'm confusing myself because I wrote it wrong. Moving this term over, the one with the dy dx. So I'm subtracting this over, x squared times 2y, or x squared 2y, there we go, times dy dx. So that the 2 terms with dy dx are both on the left, and on the right-hand side, I've got this plain 1 over 2 square root of x plus y, and then the term that was here, 2xy squared. And just this one's negative because I moved it over to the right-hand side by subtracting. So I moved this term to the left by subtracting, moved this term to the right by subtracting. And then from there, once you have the variables separated, just factor out the dy dx. And don't worry about like rationalizing denominators or getting rid of compound fractions or any of that. Just write the expression in whatever form you have it. IMathAS can understand equivalent algebraic expressions. But we'd have this whole term. I'm just going to write that over. These 2 pieces that would be, so we'd have this 1 over 2 square root of x plus y minus 2x squared y that aren't the dy dx. So in order to, this is still all equal to that. In order to solve, I'm just going to divide by all this stuff in red. So the net result looks really messy, but just a little bit of algebra. And don't try to reduce. There's not any common, like there might be a common factor of 2 you can take out from these terms, but if you do that, these are going to have 4s in the denominator instead of 2s. Just leave it like this. Don't worry about pluses and minuses. If you solved in a slightly different order, move the terms to the other sides of the equal sign, your positives and negatives would be in exactly the opposite positions, but if it's that throughout, that's just like multiplying a fraction by -1 over -1. But in any case, something like that should do the trick. So it doesn't have to look pretty, but all the calculus, keep in mind, was done by this step way up here. So the rest of this is just algebra. It's messy algebra, but it's just algebra. Distributing, combining like terms, factoring, and dividing. So the other problem that I wanted to go through was from the related rates section, just kind of the setup of the question with the cone, because I saw people had tried that multiple times and had relatively low scores still even after trying it multiple times. So let me pull that up. Let's see. Forget which question number it was. I think it was like this one? Nope. One of these here. There we go. So we've got a conical water tank with a vertex down, radius of 12 feet, at the top 26 feet high. You might have slightly different numbers, but the premise is the same regardless of the specific numbers. Related rates problems, remember, are things where there's a relationship that's known or described between 2 underlying quantities or more, and your goal is to figure out how changing one of them changes another. Because obviously, if you have a formula for area or volume or surface area or distance or whatever, if you change one of the independent variables, the dependent variable changes. If we change it with respect to time or at a certain time rate, meters per second or gallons per hour or whatever sort of rate, then the dependent variable is going to also have a rate of change with respect to time. We just have to figure out what exactly that relationship is. And it's based on the relationship between the underlying quantities, but we have to differentiate using that chain rule to take into account the time factor. So just generally here, we've got a conical tank, and if I have a cone, one thing I wanted to point out about this, I'm just going to have it facing this way. All right, so if I have a cone, pretend that this is a nice symmetric cone. Question? Yeah, so any bizarre volume sorts of formulas or areas of strange shapes that aren't rectangles would be given on the test. So make sure you know how to find the volume of a box and the area of a square, but maybe area of circle. But cones, spheres, stuff like that will be listed, because I'm not really trying to test you on your geometry recollection. I hope that you know it, but if you don't, it's okay. That's not our overall purpose. So this conical water tank has a radius that's always 12 feet. And the height of the cone, the height of the tank, I'll just write it out here so it's not scribbled in the middle, is 26 feet. Now, those aren't changing, agreed? The tank is one shape and size, and we're just filling it with water. Now, it's being filled with water. What I want to point out is, as you fill it with water, the water takes the shape of a cone. That's a smaller cone until it's full. But, you know, if the water's up to here, at this point in time, maybe the height of the water is, let's see, this asks a question about when the water's 13 feet deep. All right, so let's say that the water is 13 feet deep. What's the radius of the water? So the height of the whole cone is 26, and the radius of the whole cone is 12. These are nice symmetric figures. So if I'm at a point in the cone where I've only got a height of 13 instead of all the way filled, 26, that's not half the volume of the cone, it's half the height of the cone though. Or picturing this, if I just look at this kind of cross-sectional triangle bit, if I've got a height of 13 feet of water in the cone, but that's really within, not good at drawing straight lines. It's within this cone that if I were to take the same cross-sectional area, is like this. Do you see that those again, are similar triangles? So if I have a partially filled cone, the ratios, I guess you'd say, of the height and radius to one another are going to remain consistent regardless of how full it is, because it's always got that kind of triangular cross-section, or looking at just half of it because that's convenient right triangle. We've got, if this height is half of that, then the radius, since it's the same angle at the bottom, and these are both right triangles, this is going to be only 6 as a radius of the water at that point in time. So this is one particular point in time that we're interested in. But at either of the, like whether it's a full tank or a partial tank, if we look at a particular point in time, there's nothing that's changing. In general, this is something we're going to answer a question about. At some point of time of interest, don't know how many seconds. These all involve time, but you don't end up generally having to substitute in time. But at the time of interest, to answer our question, we might need to use the fact that the height of the water is 13 and the radius of the water at that point in time is also 6. Because it's water within this tank, that it has a nice symmetric shape, and so the cross-sectional areas are always like triangles with the same vertex angle down at the tip. So in any case, thinking about related rates problems just in general, this one in specific, but just in general, if I'm thinking about related rates problems, I need to think about what's changing. I'm filling the tank. So as I fill the tank with water, the volume of the water changes, the height of the water changes, and the radius of the water changes. Although the height and the radius aren't completely independent of one another. Like I can think of volume as a function of H and R, but H and R are related to one another. But at any point in time, all three of these are going to have one set of values that go together, and they all change together too. So in terms of thinking about what are we supposed to be finding here, eventually we're supposed to be finding, let's see, if water flows into the tank of a rate of 10 cubic feet per minute, how fast is the depth of the water increasing? So in terms of symbols related to this, the depth of the water, well, I call it the height of the water, we're supposed to be finding eventually how fast h of w is changing over time, or I'm just going to call it dHW, dt, using t to represent this generic time that we're not really going to use anywhere else, but with respect to time. So this is a change in the depth of the water or the height of the water in the cone. With respect to time, that's our overall goal. How fast is the depth of the water increasing? And then it gives us some other, when such and such happens, and that's to help us out. But we're finding the rate of change of this height of the water in the tank with respect to time when we have two pieces of information. Water flows into the tank at a rate of 10 cubic feet per minute. Water flows into the tank. That's happening all the time. This is a constant rate, so I don't have to worry about, is this true sometimes or only now? Water's flowing into the tank at a rate of 10 cubic feet per minute. Cubic feet per minute is talking about how volume changes. So we know that the rate of change of the volume of the water, not the volume of the cone, just the volume of the water, is increasing by 10 cubic feet per minute. So I'll just write 10, positive 10. The radius, it doesn't tell us how the radius is changing, but I know if the height's changing, the radius is going to be changing because they're related. But I just really wanted to point out this relationship between the height and the radius is going to remain consistent in the triangle, no matter how, or in the cone, no matter how full it is with water, because of this triangular cross-section idea, where you think of whole triangle or this, right triangle portion of it. But if I know that the volume of a cone is 1/3 pi r squared times the height, or look that up someplace since it's homework and it isn't listed right here, then the volume of the water in the cone is always based on the same sorts of things. 1/3 pi r squared, the radius of the water in the cone, times the height of the water of the cone. And you could use d for depth if you wanted to. I just avoided using d so it didn't get confused with the derivative d's. But I know I can take a derivative of volume with respect to radius or height, or maybe even change this so that it's all radii or all heights. But there's three different things in here that are all changing with respect to time. These two have a pretty simple relationship to one another. The radius of the water and the height of the water at any point in time are going to be, based on this relationship between the radius and the height. One's going to be, 26/12 of the other is 12/26 of the first. So if you want to write this just in terms of one variable, we can do that. And notice our goal is to find how the height of the water is changing, not how the radius of the water is changing. So if I could write this whole expression in terms of just v's and h's and eliminate the r's by substituting, then I won't have to deal with this r of w and dr dt, or dr sub w of t, dt, not of t. So I don't want to eliminate h, even though that would make a simpler expression, because eventually I want to find how the height of the water is changing. So if I just work on writing this in terms of just r's or just h's, in this case just h's would be ideal since we're supposed to be finding something about the rate of change of h. Here, 12, that's a value of r of w, and 26 is the value of h of w. That would be tank full height. But I could say that the radius is smaller than the height. It's 12/26 of the height, and you could reduce 12/26 at any point in time. Or I could say that the height is 12/26, no, 26/12, sorry, of the radius. But the one that's useful is going to be this one, because I'd like to eliminate having r's in this. So I could write this volume in terms of just h's, so instead of writing r sub w squared, I'm going to write, 26, or 1226 h, and then that squared. So 1226 h of w squared. So this is in place of r squared. And then you could simplify and do a more normal seeming problem from here on out. But this, again, the reason I was using those subscripts of w's is just to emphasize that it's not the cone that's changing sizes. The cone has a fixed size. That helps us. It gives us a relationship between the height and the radius. But it's really the volume of the water in the cone and the height of the water in the cone. Those things change. If you don't want to write the w's and just like understand it in your head, that's fine. Keep in mind you're just writing a final answer on the iMathAS question, but just make sure that the concept in your mind is not that the cone is changing sizes, the cone of water is changing sizes, as if it was able to stay in conical form without a structure around it. So in any case, from here, it's more like the others. I need to find a derivative with respect to time. So I'm going to leave off the w's, as I was just talking about, just to simplify this. Here, let me see if I can scoot this out of the way. So if I think of, oops, let me get this back. V equals 1/3 pi times whatever 1226 squared is. This is all just coefficients. Times h to the third power. That's just simplifying this and leaving out the w subscripts. That's kind of messy number. I'm not going to grab a calculator to work on that right now, but it's just a coefficient. If I want to find the rate of change of v with respect to time, it's going to have the same coefficient in front, times 3. Well, times 3, I know how I can simplify that. Get rid of my 1/3. And then h squared. So the 3h squared times the derivative of h with respect to t. Because again, this is h of t to the third power, just plain v of t. Its derivative is dv dt. But at this point in time, we know how the rate of change of the volume of the water is related to the rate of change of the height. Now, the only thing is it asks when the water is, I forget what the given information was here. When the water is 13 feet deep. Great. When the water is 13 feet deep, that's the same as, when the height is 13. I'm supposed to be finding this. So at that point, it's just dividing ugly numbers. But in any case, just want to point out related rates kind of as a quick test review sorts of things, and implicit differentiation. You will be doing several problems of those sorts on your test, but keep in mind some of the questions aren't like a work all the way through from start to end. There'll be some questions where all you're asked to do is kind of set up this or describe what the relationship is, or which of these, since it's multiple choice, is the proper relationship between the quantities that we need. Other things on your test, remember it goes back to since test 2, so that's like what does it mean to be finding a derivative or a rate of change in a moment? When can we find that? How do we start to do that? By approximating. And then, well, we're not going to go through the how do you find a derivative exactly, just as its own question. That was your mastery test. You know how to do that, but applications of it include related rates, our optimization questions. We went over a couple of those last class period. Our implicit differentiation. I did want to show you one other use of implicit differentiation today, just really quick, and then kind of talk about some summary information, which relates to where we actually started right after test 2. We started talking about how accumulation and rates are related back then. So, get rid of this. Actually, let me just use this. So, one more quick application of implicit differentiation. If you remember a power rule, which I hope power rule is at this point in time easy, just the general form of it, if I have y equals x to the n, we decided by looking at patterns that dy dx, or the derivative of y with respect to x, y prime, would be n x to the n minus 1. So we looked at some patterns with polynomials and binomial expansion, but we just kind of flew through and said, well, this actually works for all exponents n, not just some of them. So here's how we can do that. We can prove our power rule by using a technique that's called logarithmic differentiation along with implicit differentiation. So what that means is, suppose I have this expression. This is y, this is solved for y, or this is in function form. I can rewrite this in logarithm form. I'm going to use natural logs just because natural logs are easy to deal with. But rewriting this in terms of natural logs, if I have this expression that's true, I can take the natural log of both sides, and it's still true. And the reason that's kind of useful is because although I no longer have y equals, I have an expression where on the right-hand side, I can rewrite this with logarithm properties as instead of something with an exponent, I can write it as a product of a constant and the natural log of a variable. So I'm writing this with parentheses. This is actually just as good with absolute value signs along there. We didn't really discuss derivatives with absolute values in that, but derivative of natural log of x and natural log of absolute value x or y or whatever is exactly the same. And you know what it is. The derivative of natural log of x is 1 over x if I'm taking a derivative with respect to x. So if I take a derivative of both sides of this expression, this is equivalent. This is an equivalent way to state the relationship in the box. These two expressions are equivalent. One solved for y, the other is not. But it still describes the same relationship. If I take the derivative with respect to x of both sides of this, where n is any constant, a number, on the right-hand side, let's do that first because that's more normal looking. I've just got a constant, and then I've got the derivative of natural log of x, which we said is 1 over x. On the left-hand side, to take a derivative of this with respect to x, where I'm imagining y to be a function of x, actually I know what it is, y is x to the n, the derivative of natural log of something is 1 over that something times the derivative of that chain rule. So the derivative of y with respect to x, so dy dx. And so to finish this question, just like other implicit differentiation, we want to find dy dx. Well, if I solve for dy dx, I'm going to multiply both sides of this equation by y. And if I do that, what I get is dy dx equals n times, well, 1 over x times y. Now, y is equal to x to the n. So I could write it as n times 1 over x times y. That doesn't look like the rule that we had before. But since I know actually how to explicitly define y as a function of x, y is the same as x to the n, I could write this. And by simplifying this right-hand side, 1 over x times x to the n, no matter what value n has here, this is going to be the same as x to the n minus 1. So I've got this constant n times x to the n minus 1 power. This is x to the negative 1, x to the n power. And here's our familiar power rule coming out from implicit differentiation. You can do similar things to kind of prove why exponent or logarithmic rules work. If you can prove one, you can get the other. Now, we didn't actually prove either one of those. We just kind of looked at them. But one leads to the other because of this, again, relationship by logarithms. All right, in any case, I just want to show that because we did just, power rule is important, and it's easy enough to prove if you know about implicit differentiation. If you don't, it doesn't really make any sense. But this is also a trick that's used lots of times, rewriting an expression in a different form that's more convenient or that's easier to look at. Because this, instead of having an expression with an exponent, I have an expression with logarithms, which seem messier, but I know how to take derivatives of logarithms. If we assume that we know the logarithm rule for derivatives, then the rest of this follows. All right, so other things. Back to where we were at the end of test 2. So let's see. Here, this is something that we actually looked at earlier. We looked at this right after test 2, a long time ago. So I don't want to actually go through all of the details to this, but if you remember, right after test 2, we talked about, okay, so if this is the rate at which concrete is poured during construction of a skyscraper, how would I write a function that gives the concrete pour rate? Actually this one we talked about after we talked about derivatives. It's like, well, v of x is 30 times something. It's an exponential function. So I know how I could write the rate of change by writing r sub v of x equals, and then using derivative rule. I've got a coefficient of 30, or a constant multiple, and then the derivative of this inside function, I'd have, well, the 1 goes away, I'd have negative e to the negative x over 15 times the derivative of the exponent, which is negative 1/15. So that's not a neatened up version of it, but I mean, I could reduce the 30 and the 1 over 15 and the two negatives and so forth. But if I wanted to write, here's the point, the open form function for the volume of concrete poured, in this case for part B, and part C is something else. So at part B, starting at 10 seconds past the start of a pour, well, L of x, how much has been poured? The concrete's being poured at this rate. If I want to know how much has been poured since time 10, or since x equals 10, x is the number of seconds since the start of the pour, well, what happens because of this rate? Well, r sub v of x, I'm just going to write the symbol for it here, at every moment x since time 10 up to mystery time, I accumulate a little bit in each extremely small interval of time. I can think of them as dx's. For any small change in time dx, I have a rate that's associated with it, where x's go between 10 and, well, something. Now, we talked about this before, but our goal was to write L of x, since it said, oh, x is supposed to be the independent variable of the function here. I don't want to actually use x inside. I'll use something else. Remember, I'll say this goes from 10 to x, but that means I can't use x's inside also, so I'll say r sub v of t dt. Or this is just what happens since time 10. If I wanted to express what happened altogether, I'd have to know, well, how much concrete do I have at time 10, and then what happened afterwards. So v of x tells me how much concrete I have at any point in time. This is my volume of concrete at x seconds after the pour. So L of x is part of that. L of x is just smaller. V of x is altogether. If I take L of x and add what happened during the first 10 seconds, then those two are equivalent. Or I could say alternatively that v of x minus v of 10 is the same as this L of x that I've got. So just a way to relate these. And you had some iMathAS homework about this sort of thing also, expressing how a net change between 2 points in time is related to some other change, whether it's a net change over a longer period of time or a total accumulation starting from forever ago. But at any point in time, this is something that we did back, I don't know, at least a month ago, I think. Or the rocket basketball thing. We did the same sort of thing with that, expressing the accumulation of height or the change in the height between 2 points in time, where we had between time 4 and time 5.6, oh, well, we have this rate of change. This one was, the velocity was given. That was like the start of unit 2, like the start of before test 2. This was a rate of change. At the time, we didn't know how to find derivatives, so we started from a rate, and we used that rate to estimate height using constant rates for small bits of time, and then added them all together, and we went from that sum into eventually an integral by talking about that. If I want to know how much height changes between, ooh, sorry about that, how much the height changes between time 4 and 5.6, I want to know what accumulates between time 4 and time 5.6 due to the rate, which was v of t, changing with time values between 4 and 5.6. Or if we had a height function, so if the height is given by h of t, not to go through this whole thing again, I could express the same net change between 2 points in time by saying, oh, well, that's the height at time 5.6. This is something we did like the second week of class, minus the height at time 4. If I had a height function, and and I want to know how much the height changed, I would just subtract two values of it. If I don't have a height function, I need to know what accumulates because of the rate of change during that interval of time. So these two expressions are equivalent when v is the rate of change of h. So jumping forward to today's task, this one. All right, so that looks scary. Sorry. Jumping back to here. There we go. The fundamental theorem of calculus we talked about before, and it's exactly what I was just talking about with the rocket basketball thing. So we can express net change or accumulation during an interval two different ways. If I have an accumulation function and I want to express the amount of change, I just subtract the final and the initial values. If I do not, if I have a rate of change instead of the accumulation and I want to express the accumulated change or the net change between 2 points in time, then I write an integral expression with that rate instead. So I can integrate a rate to find accumulation, or if I actually have an accumulation function, I can just subtract two values of it. In either case, they find the net change, or the change between 2 points in time. These are equivalent to one another, and this is what the fundamental theorem of calculus says. Well, usually it says it two ways. Once this way with thinking about numerical values for the beginning and end of a time interval, or whatever it might be, an interval during which this change occurs. But it doesn't have to be. It could be in general, and this more models our total accumulation function. This here, if I imagine a rate function starting accumulation at a and going through any time x, then I can say that that's equal to this accumulation function x minus the accumulation that had happened by time a, which this order of things is maybe a little bit weirder when we've got the x in there. But I could say that f of x, oops, let me do this, f of x is equal to just, oh, well, whatever happened before time a plus what accumulates after time a up until any time x, where this is the rate of change of function f and t is our dummy variable, not meaning it's meaningless, but just it's something that's temporarily there. We let t vary from a to x for any value of x. So just with the a's and b's, that's one way you'll see fundamental theorem of calculus written, and with the a's and the x's, or whatever letters, a variable as opposed to a parameter as the top limit of integration, that's the other way that we'll typically see this. So just keep in mind that the total accumulation at time a, this doesn't have to be zero, it can start from anywhere. Just like the light that we were talking about, like the light turns on, there's already some concrete that was there to start with at that point in time, and just some more accumulated afterward. And sometimes we use something like this because the rate isn't constant, or it isn't predictable prior to some point in time a, and so we start from an amount and then we use a rate that we know works after that point in time. But other times it's just because we have some data already and we're just going to worry about later on and not so much the earlier part. So, oops, let me clear that off there. So again, I get this integral relationship here. If I talk about the accumulation of small changes between a and a general x value, I can express that using the rate function, using an integral, or using the accumulation function f and just subtracting two of its values to find change. So we talked about this a little bit earlier also, but if I have this 3x squared minus x as my accumulation function f, I know its rate of change, easy enough, 6x minus 1. So this expression here, just thinking about what its meaning is, this is talking about an accumulation that occurs between 4 and a general x due to this rate. But I know that that's the rate of change for this f of x up here. So that's actually handy because, come on, because, well, I know that I can express this a different way using this mechanism, changing it from an integral of accumulation to subtracting two values of the associated accumulation function. So I can say, oh, well, this should be the same as f of x minus f of 4 then. So f of x is 3x squared minus x, and f of 4 would be 3 times 4 squared minus 4. So this is just some number at the end, and you don't have to do the arithmetic to calculate out what it is, but it's just 3x squared minus x, and then looks like it'll be minus something, but whatever it is, it is. So I wanted to point out one thing about this, though. This 3x squared minus x is not the only function that has this as its rate of change, but that doesn't actually matter here, because if we're talking about what accumulates due to a rate, there's lots of things that have the same rate of change, but the accumulation during specific intervals like this is going to all be the same. So what I mean by that is, for instance, if I had a function g of x equals 3x squared minus x plus pi, would you agree that this has the exact same rate of change function as f of x does? Because that pi doesn't change anything about the accumulation. So in terms of, well, why do I not care that I just picked this one? All you have to do is find something that accumulates at the given rate, because the part that isn't changing isn't changing. If I were to write the same expression with g of x minus g of 4, because g of x has this also as its rate of change, I could call this r sub g of x. Well, g of x would be 3x squared minus x plus pi. And g of 4 would be 3 times 4 squared minus 4 plus pi. The pi part didn't change. That's why it's a constant. Constant didn't change, so if I'm modeling the change, I don't have to worry about constants, because constants don't change. All the rest of it, the parts with the variables, are the ones that changed. So the pi here, in essence, would cancel itself off. So in looking at a way to express an integral by doing an accumulation function and a subtraction with that, finding a net change by subtracting two accumulation function values, it doesn't matter which associated accumulation function you think of. Think of anything that has that as its rate function, anything you want, and the results will come out the same in terms of how you express that afterward. It might look different in unsimplified form, but they simplify to the same thing. And it doesn't matter whether this is from 4 to x or 4 to 7. The same principle applies, that all you have to do is come up with something, anything. Come up with the simplest one you can. Why make up a constant of pi? In order to express what accumulates for this integral here at the rate 6t minus 1. Yeah? So the closed form is this stuff on the right. The open form is this. So this is an open form, and this is a closed form. So the open form is that representing all the different computations that are involved, but not necessarily something that can be done in a finite amount of time. So there's these integrals, or when I have unstated kind of parameters that we're imagining getting close to 0, like we did with derivatives and the h's, those I can think of as being an open form, or not quite usable in their current form, but it expresses what's happening, expresses a relationship, whether it's in the derivatives, the quotients of two changes, the change in the dependent and the independent variable, or in this case, all the different infinitely many rates times a small increment of time, change in the independent variable, generally speaking. So those open forms are the integrals and the things, like the sums that we use. Closed forms are the nice normal sorts of, oh, here's a x squared minus sine of pi, or something like that. Those sorts of things are the closed form, just vocabulary-wise, when we're referring to these. All right, so I'm going to skip ahead to something in particular that I want to take a look at. All right, so notice these expressions here, they don't have any starting and ending points on the integral sign. All that means is that we want to generally express between any 2 points. So like instead of a to b, this is like kind of from x1 to x2. Like I want to express in general what the accumulation functions look like that have this rate of change. So it's actually asking you for less information, like do less, but come up with the simplest sort of expression you can have that would have this as its rate of change. And this is something you're going to focus on more in Calculus 2, the how do I find this accumulation function from the rate. But I picked a few that are maybe kind of easy to work backwards. Think, what would this be the rate of change for? So this 3x squared would be a derivative of something like x cubed. So if I think of this as r sub f of x, then maybe I'd say, oh, f of x is x cubed. So r sub f of x. Now, there's no notation in this, so I'm inserting some extra stuff that you won't generally see. I don't have to name things here. But this isn't the only function that has that same rate of change like we just talked about, and this doesn't say between 2 points. These are what are called indefinite integrals. They're kind of like half problems. It's not really it doesn't give us a result for anything, so the notation is kind of vague, but it's just generally expressing accumulation functions that have this rate. So they're all like x cubed. They could contain other constants. And so generally, what's done, or how you can think of these, is saying, well, what is the family of functions like that has this given integrand as its rate of change? Oh, well, it'd be all of the form x cubed plus a constant. And so since this wasn't actually named, and this, I don't have to call it f of x, what you'll typically see just done for these is say, oh, without any extra notation or naming, just say the answer to this. It's like, all right, what is this expressing? This is expressing things like x cubed plus a constant. And the most general abbreviation for that, so you don't have to write out a word, it's just c, but just to represent, plus any constant, or call it, this is just a parameter that we don't really have to define. We're not worried about a value of it because this, as I said, this isn't a full problem. It's just, this is an open form of accumulation. The closed form are all going to look like this, regardless of what you might want to call them, like call them function r sub f or dy dx or whatever they might be, and then here's the original f or y or whatever. Without naming them, these sorts of expressions, if it says find the integral or integrate, that's just asking you to explain what the family of functions are like, whose rate of change you can see, or in other words, write the closed form type of function that goes with this. So this t to the 1.3, that was from our velocity function for the rocket basketball. A little bit harder than the previous one, but I think we talked about this earlier on. If I took a derivative of something and it ended up with t to the 1.3 power, the original must have had a t to the 1 higher power. Right? Now, this isn't done yet. And again, all of this kind of messing around with trying to find these anti-derivatives, finding a derivative using derivative rules, is something that's going to be a main focus of part of Calculus 2. But just thinking about this in general, like t to some power, there would be a constant involved just like before. But this isn't quite right, because if I took the derivative of t to the 2.3 power, it'd be 2.3 times t to the 1.3, the n times x to the n minus 1. So we kind of compensate for the coefficient by dividing by it like that. So now if I take the derivative of this expression with a coefficient 1 over 2.3, not a nice number, but again, don't worry about the form of the answer, more just the content of it. The derivative of this would not involve a coefficient of 2.3 by the time we're done. That would get reduced out, and we just end up with t to the 1.3 power by using power rule on this. So each of these is kind of similar in that the first four are all power rule sort of situations, because each of these are power functions, powers of a variable. If I want to undo power rule, I'd have to increase the power by 1. And then think about what number would need to be in front so that if I took the derivative of this w to the 10th, it would end up being 5w to the 9th. Well, if I throw a half in the front, when I take the derivative, I get 10 times a half. That'd give me a 5. Power reduces by 1. So it's just a kind of getting used to, you could write this out as a rule, but instead of trying to come up with a rule, you can just kind of see the patterns for what you need to do to make the coefficients come out the way you want. It generally involves reciprocals. Is undoing what we do going forward. When we go forward, we multiply on the old power. If we're going backwards, we're dividing out some number that was a power in some place. But just this last one, a little bit different. It's an exponential function. You know, exponential functions, when you take their derivative, they just generally stay the same. So if I took the derivative of e to the 4b power with respect to b is the independent variable here. I can see that from the db. If I took the derivative of this, it'd be e to the 4b, and then chain rule, times 4. I've got a 5 instead of a 4 here. There, that'll put on a 5 and get rid of a 4. So this kind of like reciprocal, that over 4 aspect of it. This 1/2 here, you can think of, oh, I want to get rid of the 5, or I want to get rid of a 10 and end up with a 5. It's that same sort of idea, maybe easier to see when it's not something that reduces quite so much. But if you, this is kind of like a guess and check situation, like, all right, what do I need here? Then try taking the derivative of it. Oh, if I take the derivative of anything like this, and this plus c is a remnant of like the sort of question that this is, it's asking for a general sort of what has this as a derivative. Anything like this does. So in any case, next time is our test. Your test doesn't involve this sort of thing. This is kind of post-test fundamental theorem of calculus wrap-up. Next time in class, we're going to talk about a couple of different weird ways we can use integrals to express other sorts of things. But just kind of finalizing. Make sure you bring a calculator, and I will see you on Wednesday.